All right, hope you're all ready for this exam review, and please pay attention and then take good notes uh, about the material that I'm discussing right now, and they are important for your semester 1 exam. So let's start with the first aspects of physics that you've learned. You must know the SI units for the quantities, basic as well as derived. Now, you should be able to say what are the basic units, what are the basic quantities and their corresponding units. The basic quantities and corresponding units, you know about mass, length, and time as the most important ones. And then, of course, you have other ones like temperature, quantity of substance. So you should be able to review all those materials: temperature, quantity of substance, and electric current, and so on. And mass is measured in kilograms only, and length is measured in meters. Time is measured in seconds. Okay, so these are the most important ones, and after that, all the other ones also follow. Now, derived quantities are quantities made up of two or more of these. And so when you say derived, it's going to be like speed is a derived quantity because it's distance over time. So when you say distance over time or rate of change of distance, so delta x over delta t, that is the rate of change of distance. And the rate of change of distance, the unit is always going to be meters per second, because meters here and seconds here. So it's going to be meters per second. Okay. The delta here stands for a change in, a small change in. So delta is used to say a small change in x over a small change in t. That gives you the instantaneous sort of speed at that moment. Okay, so likewise we have so many other derived quantities, and these are the derived units because it's made up of two or more of this. Through the course we have learned so many other derived quantities, right? Velocity, acceleration. So the acceleration's unit is going to be meters per second square, and you've seen so many other quantities like force. So force is a derived quantity and is measured in newtons. Although it is a single letter, that's also a derived unit. And if you break it down into these terms, that will become kilogram meters per second square, because force is mass times acceleration, and that's why we get this. Okay. Then we went through conversions. You should be able to convert numbers, convert quantities from one set of units to the other set of units. So we saw the different prefixes used. So the prefixes that we used were like meters, kilometers, megameter, gigameter, etc., terameter, and on the lower side we had decimeter or so you have decimeter, you have a centimeter, you have millimeters, you have micrometers, you have nanometers, you have picometers. So these are all prefixes for a certain quantity. And centimeter means 1/100th of this. So this is the main thing. So I'm using meter as one of the units that I'm discussing about. So this is 1/10 of a meter, decimeter. This is 1/100th of a meter, Okay, this is like 10 power minus 2, this is like 10 power minus 3, and this is like 10 power minus 6, this is like 10 power minus 9, and this is like 10 power minus 12. And on this side, this is 10 power 3, this is 10 power 6, this is 10 power 9, this is 10 power 12. So you must be able to use these conversions. Now, these are not supposed to be on your note card. This is not a formula. So on your note card, you can put formula down, but you're not supposed to put any other numbers and stuff like that. Okay, so yeah, so these are the prefixes. And you can see how to change from one prefix to the other prefix, or simply from, so what is, if I have to look at micrometers, what is what is 50,000 micrometers? How many meters is this? So 50,000 micrometers, how many meters? So what you have to do is just take the micro. The micro simply means 10 power minus 6. So if you put 50,000 times 10 to the power of 6, that should get you an answer, and that will be in meters. So, or you can work backwards, 10 power minus 6. So go from here, 1, 2, 3, 4, 5, and 6. So the answer is 0.05 meters. So if you plug this into the calculator, that should give you the answer. And the other thing that you can see is this: when the unit goes bigger, this is a smaller unit, this is a bigger unit. When the unit goes bigger, the number has to go smaller by the same factor. Okay, so go through those areas, and then we went to kinematics. And in kinematics, the basic terms like speed, velocity, and when you say speed and velocity, you can express them in the form of graphs. So you should first of all know the speed and velocity definitions. So if I draw a graph of distance or displacement versus time, on the displacement versus time, displacement is a vector quantity, it has a direction, and therefore when I draw a line like this, it means constant displacement. This is displacement, and this simply means that it is a constant displacement. Now, the slope of the line, so this simply means constant displacement, but the slope of this line represents slope of displacement time graph is supposed to give you velocity. Okay, and what is the slope of this horizontal line? Is 0. Since the horizontal line represents 0 slope, so it's 0 velocity, that's why it's at a constant displacement. Now when you have a line like that, that means it has a positive slope. That means it's going with a positive velocity. If you have a line coming downward, that means it's a negative velocity. Because the slope is negative for this line, so that is negative velocity, and this one is a positive velocity, and this one is no velocity. So that's for a displacement time graph. Now if you want to talk about a graph that is instead of displacement in time, if you draw a velocity and a time graph, then this line here will be constant velocity, but the slope of this line represents slope of velocity time graph, will give you acceleration. So the slope of this line is 0. So zero acceleration. That's why it is moving at a constant velocity. Now if you take a slope of this line, it has got a positive velocity, which means it's got a positive acceleration. Now a slope of this line will be negative, so which means negative acceleration. And that's a positive acceleration. So each and every line, each and every line that is drawn on a velocity time graph or a displacement time graph, it makes some sense. Okay, and then so looking at graph, you should be able to make some judgments. So that is something that you should be aware of. The other areas that you need to focus on, so when we talked about the graphs, suppose you're talking about a velocity time graph. If you talk about a velocity time graph, and if you're given a graph like that, if you're given a graph like this, and if you're asked, what is happening here in this region? And the answer is, it's moving at a constant velocity. That means it is moving at a constant velocity here and a constant velocity here. Now, what is happening at this point? At that point, the velocity is not constant velocity, it's decreasing. That means it's decelerating. And the velocity is increasing from here to here, which means it's accelerating. Now, comparing deceleration and this acceleration, which one is bigger? The numerically bigger definitely is this one because it has a big slope. Higher slope, more steep, so it has a bigger value for acceleration. This acceleration is negative, but it is smaller than this. So because the slope of this line is kind of little, slightly flat, so this is slightly flatter than this. This is very steep, and so this one's slope is higher. This one's slope is smaller in magnitude, and naturally this is negative as well. And on a velocity time graph, you know that the total area of this entire graph is supposed to represent the displacement, how far it went. So this area of the graph is displacement. Okay, hope these things are clear. You should be able to recognize these things. Now, when you talk about vectors, when you talk about velocity and all that, you are talking about vectors. Now, vectors are quantities that have direction and magnitude. So when you are actually representing a vector, you are represented by means of a arrow, and so that is vector 1. And you can have another vector any way you want. So you can have another vector. If another vector is like this, v2, it's very easy to add these two together. When you add them together, it is just like v1 plus v2 because they're both in the same direction. But if they're not in the same direction, if v1 is this way and if v2 is this way, you cannot add them straight away. You have to add them by using vector methods, which is v1 and that is v2. So this will be the result, and this is how you add them. So to get this number, you have to use Pythagorean theorem to get this answer. And you can also figure out the angle by using the tangent. If you use tangent of theta is this over this, you can figure out the angle as well. So make sure that you treat velocities and all those vector quantities with respect, because if it is in the same direction, it's easy, add them. If they are in opposite directions, then just subtract them. And if it is at right angles, then you have to use Pythagorean theorem. Okay. So sometimes those questions can be as simple as, like, suppose this is a river that is flowing. If that's a river that is flowing in this direction, and you want to cross the river from here to here. So you want to, this is a point which is directly north, okay, and the river is flowing this way. The river is flowing from west to east, and you want to swim across like that. So you're going to swim to the north. So if you are trying to swim in this direction when the water is flowing this way, will you reach here? You will not reach here. So where do you think you will end up reaching? Because the water is flowing this way, every time you attempt to swim forward, you're going to be shifted this way. So this is where ultimately you will end. That's where you will ultimately end. If you're just blindly swimming straight across, the water will take you sideways. So you'll end up here. So this is how much the water takes you, and this is how much you go. So the resultant is this. That is where you end up. But suppose you want to really go and touch that point. If you want to really reach here, and the water current is also existing, so how do you reach here in spite of the water? So the water is flowing that way. So if you swim straight, then it'll go here and you'll end up here. So to beat the movement caused by the water, you have to tilt yourself like this. So if you swim in this direction continuously, the river takes you that way, and ultimately you will end up going straight. So which way should you be swimming? You should be swimming, that's a north, that's a west, that's a east, and that's a south. So which way are you going to be swimming? You'll be swimming west of north. Some angle west of north. You're not going to swim north, but you're going to swim this way, which is to the west of north. Okay? So that way you can figure out which way should you swim in order to reach that particular destination. And then your regular equations of motion. So you know the equations of motion. Let me list it down here. Vf is equal to Vi plus At. Vf square is equal to Vi square plus 2Ax. X is equal to Vit plus half At square. These are the equations, and you can also write 1x is equal to Vf plus Vi over 2 times time. So these are the equations of motion, and how we use them depends on the situation. Now you can see that every equation has 4 terms, and therefore if you know 3 terms, you can figure out the 4th one. And there's always something missing in the equation. This is missing in displacement. This equation is missing in time. This equation is missing in final velocity, and this is missing the acceleration. So if you're given a certain question, you need to use one of these equations to get to the answer. So for example, if I drop a stone from the top of a building, and the building is like 10 meters tall, so how fast is it going to strike the ground? How fast is it going to be moving when it strikes the ground? So if you want to find this out, your initial velocity is 0, you dropped it. You want to find the final velocity, and you know this is a displacement. So if you look at it, displacement is given, initial final velocity is known, and acceleration is negative 9.81. So once you have 3 quantities definitely known, you can figure out the 4th one. And so the stuff that we don't know here is time. So pick an equation without time, which is this, and then use it. So Vf square is equal to Vi square plus 2Ax. Vf square that is what you want to find out. Vi square is 0 because it started from rest. And then it's 2 times negative 9.81 times displacement. From here to here, the displacement is minus 10. And then if you work this out, you get Vf square, and then Vf is equal to, take the square root, meters per second. So this is how we solve for such things. So whatever be the objective, now in this case the final velocity is the question. If you're asked what is this, what is the distance traveled down there, if they don't give you the distance, then you have to figure out a way to do it. But in all problems, at least 3 quantities will be given to you, and you have to pick the proper equation. Okay, you have to pick the proper equation to go ahead and work it out. So that is how we use equations of motion. And then so you may have a couple of questions on equations of motion. Okay. Average speed and average velocity, that concept. Average speed is a total distance over total time. Average velocity is the total displacement over total time. When you say displacement, when you go around a circle and come back, you made no displacements. You're back to the same starting point. So average speed and average velocity definition are these, and you should be able to work problems using this concept. Now, if the units for distance are given in miles or kilometers, you must know how to change it to meters. Similarly, the time, if it is not given in favorable units, you have to change it to time in seconds. Only then you can get your answers in the right unit, meters per second and meters per second. Okay, now moving on from that chapter to Newton's laws or projectile motion. So projectile motion, when you say projectile motion, it's also going to be using equations of motion, but this time you're projecting something at an angle. So when you project something at an angle like that, it actually goes and comes back here. So some of the concepts that you need to know is when you're projecting something with a certain velocity at a certain angle, then you need to split this into 2 components, which is how much horizontally it is going, so it's v cosine theta. How much vertically is it going, it's v sine theta. So once you split it, you should understand one concept, that is, this horizontal velocity never changes. It continues to go on, go on, go on. The horizontal velocity never changes. But the vertical velocity is the one which changes. It actually becomes smaller and smaller, and finally it becomes 0 here. Vertical component becomes 0, and then here it actually switches direction. It starts moving faster and faster and faster. So when it comes and strikes here, it literally comes and strikes with the same velocity with which it was projected. Okay, so this is a concept here. So what is happening? How fast is it moving at the very top of the trajectory? It is moving at the same speed as the horizontal component v cosine theta. So the speed here is v cosine theta. Now generally in these kind of problems we just make the table horizontal, vertical. So put the horizontal components here, horizontal displacements here. So this is a horizontal displacement. The vertical displacement is that one. So you put the horizontal displacements, horizontal acceleration and all that, initial velocity, vertical. Now this is all to do with vertical. So you do all that stuff vertically. At least if you know 3 things on one side, you can figure out the 4th quantity. And once you have the 4th quantity, you should be able to work through the rest of the problem. So that is the basic idea of projectile motion. The acceleration, once the projectile is thrown already, the acceleration that it is going to be undergoing is always negative 9.81 because it is falling. It's falling freely all the time. Okay, so the acceleration from here to here is 9.81, negative 9.81. At the very top, it's still the same thing. So just because it stops vertically Doesn't mean acceleration is 0. It is negative 9.81. Okay. All right. So if you're given forces, now let's go to forces then. In forces, what you need to know is force is a push or pull, and there are contact forces, and there are field forces. Contact forces and field forces. Now, contact forces are forces which needs the proximity of the two materials. So a normal reaction is a contact force. So when you push physically something, then that's a contact force. When I write on this paper, that's contact force. But field forces are forces that can act from a distance, like gravitational force, nuclear force, electrostatic forces, and all those things are actually field forces. They don't require a physical contact. The other one requires a physical contact. Okay. Now, the most important thing you need to know here is the first law, the second law, and the third law. The first law of Newton, as you must have written down in your notes, is the inertia law, right? So the inertia law, what is all about inertia? Inertia is the tendency of an object to stay in the same state of motion. So Newton's first law says every object tries to stay in the same state of motion unless acted on by external unbalanced forces. So that's the first law. The second law is a law which talks about acceleration. So when an object is going to accelerate, it accelerates in such a way that it follows that equation F is equal to ma. So when I push an object of mass m, it will accelerate to only a certain extent because it will accelerate only to some extent because it will depend on the mass, it will depend on the force that you apply. So that all those are important. Now, so F is equal to ma is the second law. Third law is talking about the pairs of forces. These are called the Newton's third law pair. For every action, there is an equal and opposite reaction. So the action and reaction pairs is what we talk about. And a typical pair is this. If you're talking about a book sitting on a table, the book is pushing the table down because of the contact. There's a push by the book on the table. And the pair for that, this is the contact force. So it's a push on table by book. And the other force is push on the object, by the table. So you can see in one case it is acting on the object and the other case is acting on the table. And this is by the table and this is by the book. So these are the action-reaction pairs. Action and reaction pairs. They are always opposite, they are always equal, they act at the same time of action, line of action, they must belong to the same kind, and all those, and they are opposites. So they must be acting in the same line of action. So all those points simply tell us that this Newton's third law pair, they are equal and opposite to each other, and they will never be able to cancel each other. So keep all that in mind. In projectile motion, we have a projectile motion that is horizontal projection, something that goes like that. So keep in mind what happens when it goes from here to here. It basically is falling, but because we gave it a horizontal velocity, it is falling into a different area, different spot. So how we tackle this problem is by the table method. So you make the table and then put all the details and solve it. So go through your home class notes and all that to see how such problems are solved. Okay. If you're given angles, then remember to use your calculator with the angles. Make sure your calculator reads in degrees, otherwise the whole thing can be messed up. Okay. When we talked about Newton's laws, we saw the first one is the inertia law, and the second one is the acceleration. So F is equal to ma. F stands for the net force. So if you have two forces already acting on an object, we have to take the net force and equate it to ma. Okay, then you'll be able to figure out. Now, when you say Newton's third law pair, you push something and the other object pushes you back immediately. So those are the pairs. And those pairs are supposed to be equal always. So remember in the quiz that you had a question, you know, if a car and a bus comes and hits each other, which one is going to offer a bigger force on the other? It's the same because they are Newton's third law pairs. So it doesn't matter whether a car is hitting a bicycle or a bicycle is hitting the car, the force that one offers on the other is always going to be the same. That is Newton's third law pairs main idea. Okay, and moving on from there to energy concepts. So, you know, these are all the concepts, you must be familiar with them. Now, energy concepts. You already know that energy and work are related terms. So work, energy. If you do work, you are producing energy. If you have energy, you are capable of producing work. So using your energy, you can actually push something and do work. And you know the work done formula is F d cosine theta is the general equation. But F work done will be equal to F d if the force and displacement are in the same direction. If the force and displacement are in opposite directions, then the work done is minus F d. If the force and the displacement are at an angle like this, then you use the above equation, because what is happening is we are splitting this force into two components, a horizontal component which is d cosine theta or F cosine theta. F cosine theta gives you the horizontal component, and then you multiply it by the displacement, and that will get you the work done. This vertical component of F sine theta does not do any work. Okay, keep that in mind. And FD, the concept is clear. The unit of work is joule, which is the product of force and displacement. So basically joule is Newton times meter. And if you break this joule down into basic terms, you get kilogram meter square second to the power of minus 2. So this is basically the same as a joule. And when you do work on an object, the object can gain kinetic energy or potential energy. Kinetic energy formula is half mv squared. Potential energy formula can be different according to whether you're talking about GPE. If it is GPE, then the potential energy is mg delta H. And if you're looking at the other form of energy, which is half kx square. So elastic potential energy is half kx square, where, as I mentioned in class, k is the force constant of spring, and x stands for the extension. X stands for the extension. So half kx square, k is the force constant of the spring. Different springs have different k's. A slinky probably has a very small k, and a car spring is supposed to be having a very, very high k. Okay. So you know work, and you have kinetic energy, and then power. Power is the rate at which work is done. Power is the rate at which work is done. So power P is work over time. Power is work over time or energy over time. Power is work done over time or energy over time, and the unit for power is joules per second, which is what we call as watts. Work done is FD. Okay, so if you take this power is equal to work done is FD, and time is divided by time. So FD divided by time is power. Okay, and if you look at it one way, the displacement times time is velocity, so power is force times velocity as well. You can actually have that. And beyond this, I want to introduce you to what is known as momentum. When something moves, a moving object has kinetic energy. A moving object has kinetic energy because it's moving, and the kinetic energy is half mv squared. Similarly, a moving object has what is known as momentum. Momentum is dependent on two quantities, which is mass and velocity. Because the more the mass, the momentum will be higher. It's like having more inertia. So momentum of an object which is moving depends on the mass. So a football player with a good mass, if he's running, you can actually say that he's running and he's going to carry his momentum with him. So that is the word momentum. So momentum is m times v. The unit will be kilograms for mass and meters per second for velocity. So mass times velocity is momentum. Okay. All right. So you know that part of it. And going back to power once again. Power is work or energy over time. Okay, power is work done over time. So let's say if I have a table and there are lots of bricks on the floor, and if I ask a kid to take these bricks and put it on the tabletop, the kid will be able to take these one by one, and finally put all those bricks on the top of the table. Now on the other side, I have the same number of bricks over here, and I ask a bodybuilder to do the same transfer. So when I told the bodybuilder, he grabs all these bricks in one go and puts it there. So all the bricks come back here. Now my question is, who has done more work? This is a child doing work, and this is the big man. Who has done more work? The child putting the bricks there, or the muscular person putting the bricks all together in one go? Who did more work? In fact, they did both of them did the same work, because the bricks moved from here to here. These bricks moved from here to here. So they both did pretty much the same work. Now, who is more powerful? The one who did it in the least time is more powerful. So power is regarded as the how much work is completed in how much time. All right. So that is the power concept. Now, when things collide, like cars or anything collide, collision, take notes on this and this quantity. Collision, there are two kinds of collisions mainly. One is called elastic and the other inelastic. Elastic collision is a collision where the objects will bounce and move away. The object is going to be moving away after the collision. So when you have collisions taking place where the total kinetic energy before and the total kinetic energy after, the total of the kinetic energies should stay the same. So kinetic energy is conserved. If that's the case, then that collision is elastic because there is no loss. An inelastic collision is when the two objects will collide. Sometimes they can get stuck or they can bounce with smaller velocities. So in that case, we call it inelastic collision. So what is conserved in this elastic collision? Kinetic energy is conserved. Okay. Kinetic energy is conserved. Kinetic energy before impact should be equal to the kinetic energy after impact. That is what is called elastic collision. But most collisions are inelastic because we end up losing energy in different forms. Okay. All right, so these are pretty much what you're supposed to be aware of for this test, and hopefully you'll be able to use the equations properly and process it properly, because I've seen students not able to manage how, the half. So the kinetic energy is given to you. So kinetic energy is half mv squared. There are many who don't understand how to do this, and some of you actually end up mixing a mass and velocity together. It is not mass and velocity together, it's mass separately and then velocity squared. Velocity is being squared. So don't square mass times velocity the whole square. That's not right. So this is what you're supposed to be doing, and then plug the numbers in and move these variables as per algebraic rules. Okay, I've seen mistakes in the latest quiz because of this concept. Yeah, you should know how to handle the thing. Okay, equations and how to. Suppose I gave you the kinetic energy and you need the velocity or the mass, and you need to move those quantities aside and do it, and that is what it is. Now power is work over time. As I said, power is force times displacement over time. So because work is force times displacement, you can actually use that too. Okay. Now conservation of energy. Conservation of energy. Energy cannot be created nor destroyed. It just changes from one form to another form. So if, say for example, a basketball is rolling out of that hoop, if a basketball is rolling out of the hoop, okay, let's say the initial velocity is 0 here, it just barely started rolling down there. So when it fell from there, the velocity is 0. That means kinetic energy is 0 at this point. But it has potential energy. Gravitational potential energy is mass times gravity times height. This is the height we're talking about. But when the basketball falls from there to here, it is losing the GPE. So GPE here becomes 0, and it is gaining kinetic energy is half kx squared. The sum of these two should be equal to the sum of these two. That is how conservation works. So mgh should be equal to half kx squared. Mass half mv squared. Half mv squared. Half mv squared. We can use half kx squared only if it's a spring. If it is landing on a spring and compressing a spring, then we can use that. But otherwise, half mv squared. So mgh is equal to half mv squared. Cancels, and then if you you can see this half. What should I do to get rid of the half? Multiply the whole equation with 2. So if I take the whole equation and multiply by 2, I get 2gh is equal to v squared. And then square root the answer of this, and that will be the answer. So make sure you know how to do this. Now what happens when the basketball comes halfway down and it's on the process of falling? Is the kinetic energy still 0? No, because it's already moving. So kinetic energy is something, and potential energy is something. And potential energy can be found out because if the height was h, then it is mgh. If the height is only half of the h, then it's going to be half of mgh. Okay, it's high because the height is half. Everything else stays the same. So you can figure out from what height it rolled off. Okay, so this is what I can say about the test, and now you can actually use base these points. You can use these points and search from your textbook or from your notes in the class, the notes that you've taken, and also look into the homework questions that we have done for different exercises. So these are the main points, and based on this point you can answer all the other questions. Okay, all right, so good luck with this test, and you all have a good Christmas and a happy New Year, and we'll see when you come back. All right, stay safe and do your test well.